These set of notes are going to go over intermolecular forces, also known as IMFs. So we're going to be concentrating on intermolecular forces of covalent compounds. This is the force of attraction between neighboring molecules. This would often be because of a partial positive end of one molecule attracting the partial negative end of another molecule. Now, intermolecular forces mean attraction between neighboring molecules. Just so that we're really clear, intramolecular is a different word, and that is the attraction that creates chemical bonds. So in H2O, if you're looking at H2O, this bond here is an intramolecular bond, but how H2O interacts with another H2O, so how these interact, this would be intermolecular. So intramolecular are the chemical bonds. Intermolecular are how different molecules, separate molecules, interact with one another. So we're going to be talking about intermolecular. So there are three common intermolecular forces for covalent compounds. The first one is called a dipole-dipole. Again, dipole meaning two poles, that slightly negatively charged pole and that slightly positively charged pole. So this is what happens when polar molecular molecules are attracted to other polar molecular molecules. So again, attraction between polar molecular molecules. Now, remember, polar molecular molecules often form because first polar bonds exist and because of the shape of that molecule, its Vesper. So the first one we're going to look at is a pretty simple example. We're going to look at a linear molecule of bromine monofluoride. So the first thing I'm going to notice is that bromine has an electronegativity of 2.8. Fluorine has an electronegativity of 4.0. That is going to create a dipole because fluorine is more electronegative than bromine. So that's going to create an uneven pool of electrons toward fluorine. That's going to give this side of the molecule a partial negative charge and this side of the molecule a partial positive charge. There's nothing canceling out this dipole, so this is going to be a polar molecule. Again, because one side has that partial negative and one side has that partial positive. So let's take a look at what happens when this molecule comes near other molecules that look like it. So I have a bunch of BRFs that I have drawn here. I'll just highlight them in highlighter here. So here is one BRF. Here is another. Here is another. And what ends up happening is that each of these molecules ends up interacting with one another. So I have 5 molecules here. And what you'll notice is that the fluorine has a partial negative charge. And so when it comes near the bromine of another molecule here, it's attracted to its partial positive. And then the partial positive of this bromine is attracted to the partial negative of this fluorine. And so all the partial negatives are attracted to partial positives. And all the partial positives are attracted to the partial negatives. And so they start to create these intermolecular forces that help them stick together. All right, so let's take a look at an even bigger molecule. So this one is a tetrahedral. Lots of tetrahedrals are actually often nonpolar because they're often really symmetrical. But let's take a look at this particular example. So in this example, what ends up happening is that fluorine has such a higher electronegativity than everybody else that it's pulling toward fluorine harder than it's pulling toward any other atom. So even though chlorine has a higher electronegativity than carbon, fluorine has a higher electronegativity than everybody. So there's a general pull in the direction of fluorine. And that's going to give fluorine this partial negative charge, and that's going to give these chlorines the partial positive on this end. So again, creating dipoles. So one pole is partially negative and the other end is partially positive. Now, what happens is when this molecule comes near another molecule, the partial negative side of one is going to attract that partial positive side of the other molecule. So again, this side has that partial positive charge, and this side had that partial negative charge. And so this partial negative attracts these partial positives and creates this sort of like weak intermolecular force that holds these kind of close together. So that's what a dipole-dipole is. Again, it's the attraction of these two oppositely charged poles. And those poles exist on polar molecules. The next type is a hydrogen bond. Now, a hydrogen bond is basically just a very strong dipole-dipole. So it's like a type of dipole-dipole. They're just very strong poles. And so it creates a intermolecular force that is considered a bit stronger than a standard dipole-dipole. So they like to sort of separate it out. Now, the hydrogen bond gets its name from the fact that it often is a hydrogen attracted to some other electronegative atom. So the partial positive of a hydrogen on one molecule being attracted to a very electronegative atom of a neighboring molecule, because it's always one molecule to another molecule. And you'll know that it's a really electronegative atom because it's pretty close to fluorine. So fluorine, nitrogen, and oxygen are all very electronegative atoms. So it is often the attraction of the positively charged hydrogen end of one molecule and the partially negative charged end of a molecule containing a fluorine, nitrogen, or oxygen. H2O is our number one best example of this. So when I look at water, oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So when I look at that and the fact that it has a bent shape, so it has polar covalent bonds. So there's a polar covalent bond between this oxygen and this hydrogen because oxygen is more electronegative than it. And there's a polar covalent bond between this oxygen and this hydrogen. And because it's bent, so both of my dipoles are moving in this slight upward direction, they end up not canceling out because there is no dipole moving in the down direction. So what ends up happening is I get a slight negative charge on my oxygen up here, and I get these slight positive charges on these hydrogens down here. Now this is one molecule that I'm looking at. I'll go ahead and circle it with a highlighter. And it is surrounded by these other H2O molecules. Now these other H2O molecules have a similar structure when it comes to polarity because they're all the same. They all have dipoles. They all have this sort of asymmetrical shape, so they're all creating these polar molecules. And what ends up happening is you get these intermolecular forces again between your molecules. So this hydrogen here has a partial positive charge, just like these ones do here. And it has an attraction to this partial negative charge. This partial positive hydrogen is attracted to this partial negative oxygen, and so on and so forth. So I get all these intermolecular forces between these molecules. And these ones are slightly stronger than a standard dipole-dipole. And that just has to do with the level of electronegativity between this side and these, right? So the difference in numbers just tends to be greater when you're dealing with these really electronegative atoms and hydrogen. So again, hydrogen bonds. A really nice example of this in biology is DNA. So you have all these covalent bonds that happen on this side of our DNA molecule, and we have all of these covalent bonds that happen on this side of our DNA molecule. And actually, our DNA is all double-stranded, and the two strands are actually only held together by hydrogen bonds. So there are hydrogens and oxygens that are located here and here and here and here, and they attract one another with these intermolecular forces. So these aren't strong covalent bonds, these are actually weak intermolecular bonds, but there ends up being so many of them, like thousands and thousands and tens of thousands of them, that they're actually able to keep the two sides of our DNA strand together, which is pretty cool. Sort of like how you can float on water if you spread the weight out. So if you've got water and you put a big mat across the water, right? It doesn't sink through because you have all those hydrogen bonds, all these intermolecular forces, and you've got millions and billions of them helping hold up that mat on top of the water. But if you were instead to put like a heavy rock, what ends up happening is that there aren't as many intermolecular forces that it's laying on top of. So the rock is able to sink down because it's able to break the fewer intermolecular forces because it's more dense, right? But if you were to spread out that weight, then it's on top of billions of intermolecular forces and it's able to hold it up. Anyways, we'll talk more about that later on. We've got one more intermolecular force to talk about. It's called London dispersion forces, sometimes also known as van der Waals. These are a intermolecular force that only happens with our that can happen with our nonpolar molecules. So the idea is that electrons are in constant motion, and at any instant, there's a chance that the electrons are slightly unevenly distributed, right? That's just probability. There's a chance that they're all, toward the left side of our atom. And during this time, it creates a temporary dipole or an instantaneous dipole. And so what ends up happening is during that moment when that temporary dipole forms, it is then attracted to another temporary dipole, which is pretty cool. So the London dispersion force increases with the size of the atoms and the molecules because there are more electrons that are able to shift. So we're going to look at an example of a small molecule, but with a larger molecule, it's more likely to happen. So in this particular case, this is a linear, very symmetrical molecule, and this is a nonpolar bond because oxygen has the same electronegativity as oxygen. So this is a nonpolar covalent bond. This is a nonpolar molecule. But there is always a chance that in any moment that the electrons just happen to shift, let's say generally to the right in this particular example, causing a spontaneous dipole where I get a slight negative charge on this side because they just happen to shift that way, and that means a slight positive charge on this side. Well, that means that if there is another molecule that was also having an instantaneous dipole forming, that this partial negative would then attract this partial positive, forming a very, very weak intermolecular bond or force between the two. Also, they've seen that during a London dispersion force, it can induce a temporary dipole in its neighbor. So when these shift over to the right, and this has a slight negative charge, that slight negative charge might actually push these electrons also to the right because negative repels negative. So this slight negative repels these electrons away, causing that instantaneous dipole to form here, causing an attraction between these two molecules. Again, these tend to be pretty weak, and they are broken really easily because oftentimes they are quite temporary, but these are what help geckos climb on walls because they have so many thousands of tiny hair-like structures on their claws or paws or whatever you call them. They have so many of these London dispersion forces or these van der Waal interactions happening that they're able to stay on the wall. But again, the bonds are really, really weak and potentially temporary because these could easily shift back. So again, here's another example. This is a nonpolar molecule. This oxygen has a higher electronegativity than carbon. It's pulling it to the right. This oxygen has a higher electronegativity than carbon. It's pulling it to the left. They cancel. So this whole thing ends up being nonpolar. But there is a chance, probability says, that there's just a shift in the electrons and they just happen to all be on a similar side, or most of them are on a similar side. causing a just general shift in one direction, causing a partial negative charge on one side and a partial positive on the other. This again can repel electrons, causing a temporary dipole in the molecule next to it. So we've learned about 3 IMFs. They all happen in covalent compounds. London dispersion forces are the weakest of them. These tend to be formed by nonpolar covalent molecules. They tend to be temporary, and one London dispersion force or one van der Waals interaction could cause another one, but in general, these are very easily broken. The next type that we learned about, or one of the ones we learned about, was dipole-dipole. Now, these happen in polar covalent molecules, and they're a bit stronger than these London dispersion forces, but again, still easily broken. They're all technically easily broken, but these kind of fall in the middle. And then there are hydrogen bonds, which again are sort of just a type of dipole-dipole that just got picked out individually because these are in general stronger than most dipole-dipoles. So hydrogen bonds happen in polar covalent molecules when there is a hydrogen present and also either a fluorine, nitrogen, or oxygen in the other molecule. So again, those are the 3 types of intermolecular forces, the weakest being London dispersion force, the strongest being a hydrogen bond. Now, just a little bit about our IMFs. So, we don't typically think about IMFs just one happening. We think about like lots of IMFs happening. That's why London dispersion force can explain why a gecko can stay on top of a wall. When you float on top of the water, that can be explained when talking about hydrogen bonds because of those intermolecular forces. So when we talk about our intermolecular forces, it helps us explain a lot of the things that we see happen in nature. So the stronger the IMF, the more energy required to weaken the IMF or to break the IMFs. So the more energy you would need to break these intermolecular forces compared to these. So these would be easier to break than these would. That means that if you have a higher IMF or you're a hydrogen bond compared to a London dispersion force, that you're going to have a higher melting point because you're going to have to put more energy in order to get those molecules to start to spread apart from one another, which means that you'll also have a higher boiling point. So same idea, it's going to take more energy to get those water molecules to separate from one another because their intermolecular forces are stronger than, let's say, other non-polar molecules. So they're going to need more kinetic energy in order to resist the attraction of their neighbors. Molecular mass will also affect IMFs. So typically, when things have a greater mass, they are moving slower, which tends to help them be more attracted to their neighbors just because they're less likely to move. Those intermolecular forces are more likely to be created. So solids in general have little kinetic energy and tend to have higher IMFs. Liquids have some kinetic energy, tend to have slightly weaker IMFs, and gases have a lot of kinetic energy and essentially have no intermolecular forces. The molecules of gases are interacting very little. The molecules of liquids are interacting some, and the molecules of solids are often interacting a lot. So that's some extra bits of information about when we're thinking about intermolecular forces. But in general, these are the 3 intermolecular forces you need to know, and then we'll be practicing how to determine which molecules are likely to participate in which of these forces.